Hello. When we're talking about light, in order to study something in space, we need to figure out how do we get the light to study. So that eventually comes up to be essentially telescopes. Telescopes helps us get the light. And so that's the idea. We want to understand how do we get the light. Okay, so first telescope to use for astronomy was actually done by Galileo Galilei. And so Galileo made a telescope of his own and recorded his results in the Sidereus Nuncius, starry messengers, that's what that refers to. And so the starry messenger, or the Sidereus Nuncius, that was the results of his small telescope that he built. He heard about telescopes from someone else, and he built one. He didn't invent the telescope, but he's built this, and he's noticed things in the sky. He saw, wait, the sun has spots on it. Jupiter has moons that go around it, and Venus goes through phases, and he saw extra stars in the sky. And so this started the whole idea of telescopic views, because then you could see more than you could see with the naked eye. So how does a telescope work? Basically, the way that a telescope works is that you have a lens, and then with the lens, that light comes in and is focused to a point, and then but you can't see that way, so you have to unfocus it here with another lens. And so the basic idea is that light coming in here is focused down here, so light spread out over this big area is concentrated. Well, we know from studying of light that intensity is the power divided by the area. So if you're concentrating over a smaller area, then you end up with greater intensity. And so light ends up being intensified in this fashion. And so that's what the telescope does. It makes things look brighter. Now there's also magnification involved. And so the magnification is going to be equal to the focal length of the first lens. We call that the objective lens. So that's f sub o. So it's the f sub o divided by f sub e, which is the focal length of the eyepiece. So the part you look through is the eyepiece. So you take this focal length and divide by that focal length. And so that's the magnification. So if the focal length of the telescope is, for example, 1,000 millimeters, then that would mean that the eyepiece, if the eyepiece is going to be 10 millimeters, then 1,000 divided by 10 would be equal to 100. Now, if on the other hand the eyepiece was 25, so if this was 1,000 millimeters divided by 25 millimeters, then that's different. So that in that case it would be 40. So the focal length is going to be dependent. The magnification is dependent on the focal length. Okay, so there we have it. There's the formula. So again, if you have a telescope that has a focal length here of 1,000, and the focal length can be anything, depends on what it is. If the eyepiece, you can change the eyepiece, and that will change the magnification. And so again, if this was an eyepiece of 10, be factor, then 1,000 divided by 10 is 100. If the eyepiece was 20, 1,000 divided by 20 is going to be 50. And so it'd be whatever that would be. So, okay. Kind of telescope we're talking about here is refracting telescope. A refracting telescope is a telescope that uses lenses to bend the light. Now the problem is that you have a lens at the front of the telescope, you have a lens at the back of the telescope, and so the telescope is going to be very long. For various reasons, the longer the focal length, then the better the image is going to be for a refracting telescope. And so that means your telescope is very long and very unwieldy. It's pivoted in the middle here somewhere. So this particular telescope right here is only 6 inches in diameter, but when it's looking at something down near the horizon, you'd have to stand on a ladder to look through it because the eyepiece would be up here about 8 feet off the ground. Whereas when it's looking straight up at the zenith, the eyepiece is down here and it's about 3 feet or 3.5 feet off the ground. So you have to sit in a chair to look through it. Reason that it's an issue with refracting telescopes is the light is going through a lens. Lens is a piece of glass, and we know, with a prism, for example, the different colors are bent differently. So it's possible, for example, that blue light is bent more than red light, and so the blue light is focused to a point different from the red light is focused. This is called chromatic aberration. Now, you've probably experienced this if you had a cheap little telescope and your little cheap telescope somewhere, you looked through it and you saw everything you looked at, had rings around it. Well, those rings are, if you looked at them carefully, they were different colors. And they were different colors because you had one color in focus. So you could only focus one color, and the other colors were all out of focus. And so one way of fixing that is to actually put another lens in here, and this other lens slightly defocuses the light, and it's going to defocus the blue light more than the red light, and so the attempt is to bring everything to focus at the same point. So that would be called an achromat. But it's very expensive because what you have to do is you have to get the achromat so that so you get the achromat in there, and both lenses had to be exactly equally balanced. Okay. There's another issue that comes here, and that's physical size. The bigger the telescope, then the more you have to deal with. The Yerkes Refractor is actually the world's largest refracting telescope right here. It's 1 meter in diameter here across the front of it. Yerkes actually was not the guy who built it. It was built at the University of Chicago, and a fellow named George Ellery Hale got the money to build it. Yerkes turned out to be the guy who gave him the money to build it. He made a lot of money doing streetcars back turn of the century, turn of the 20th century, and so he wanted to make a name for himself, and they convinced him to donate money to University of Chicago, and so they built this telescope in Wisconsin, and it's a huge thing, pivoted right here in the midpoint. So again, that other refractor I looked at, I showed you that telescope right there, that telescope pivoted, from about 3.5 feet up to about 8 feet. This one goes many dozens of feet when it looks something low to high. And so that turns out to be yet another problem to deal with. In fact, if you look at the picture up here, this row of windows right there, that is right here. And so the difference is that when this thing is looking close to the horizon, the eyepiece up here is going to be 30 feet up into the air. Well, 30 feet into the air, that's not realistic. So what they did was the floor of the observatory moves up and down so that you can use the telescope. So again, this is a big refracting telescope. Okay. Now, one of the problems with a refracting telescope, one of the big problems with a refracting telescope is you have to have a lens, you have to hold the lens by the edge. Okay. So you have to hold the lens by the edge. So imagine you've got a lens, you can't hold it from behind, you got to hold it around the edge. Well, the telescope lenses are very narrow sort of things right there at the edge, and so that's holding it at the weakest point. So the idea, though, was, well, wait a minute, suppose that you have the eyepiece, and the way the eyepiece worked was that your eyepiece focused light. We could also focus the light with not just an eyepiece, but you could focus the light with a mirror. And so Isaac Newton had the idea of using a mirror to focus the eyepiece, and so he built a telescope here that focused eyepiece with a mirror. Okay, and so light would come in, come up here, go up the side of the telescope. William Herschel, he discovered the planet Uranus here, and he did it with a homemade telescope. Same thing, light comes in, hits a mirror, comes up, and then goes out the side of the telescope. And so this would be a reflecting telescope. Reflecting telescope uses mirrors to focus the light instead of lenses. You can actually build it a lot larger because you can support the mirror all the way around here. And the other thing is, with a lens, both the front and the back of the lens have to be exact. With the reflecting telescope, that's not necessarily the case. The back could have imperfections in it, and the front would have to be exact. And so that's the idea of a reflecting telescope. And so the light would come in, okay, and so the light would come in here, hit the mirror, come up, and then go out the side of the telescope. There's other things that can happen. That's what we call a Newtonian focus. You could have a Cassegrain focus where the light comes in, hits a mirror, goes up, hits the mirror, comes back through a hole in the main mirror. That's a Cassegrain focus. And a Coude focus in which the light comes in, hits a mirror, comes up here, hits a mirror, comes down here, hits a mirror, then goes out the side. Now the Coude focus is nice because you can actually pivot it right there. So that'd be the center of mass. So that means a very heavy instrument sitting right over here somewhere would not have to move much. So it wouldn't be weighting the telescope. Prime focus, the light comes in, just comes to a focus. And the problem is, if you put your head right there with your eye to look at the mirror, your head would block the view. So that was not a preferred orientation right there. Okay, but bigger and bigger telescopes began to stretch the abilities. So this was a big telescope that was built in the 1800s by the third Earl of Ross, and was a huge telescope. Was one of the first ones they started figuring out what galaxies were. They looked at galaxies and they saw swirling patterns in the space. And so this was so huge that the astronomer would stand on a platform up here and then look in the side of the telescope, and he would motion to his assistants, and what they would do is they would have ropes that just move the front end of the telescope.